To my viewers around the world,
to y'all.
remember, get your family and friends to subscribe, and you get their Oreos if they subscribe. How about that? Finder speed. All right, that's enough of that. All right, let's look at this. This is lesson 4, 3, 2,
1.
Good. Probability with combinatorics. So this is talking about combinations or permutations. The main idea about this, and this is review, there's really no new concepts. It's just how we're applying combination permutation to a probability event. So I want you to think about this. This is key. This is the review. Probability of an event is equal to the number of ways the desired event can occur. That's what you want to happen. Divided by the total number of events. The total number of events. So if I look at this, I'm pretty sure that most of the time, if I'm using combinations or permutations with this, I'm going to be figuring out that total number of events. Because remember, if we have B, D, we'll go U, right? We have 3 tiles here. There's ways, a bunch of different ways we can arrange it, and I could go here and just try to strong arm it, figure out how many ways. But if I didn't want to do so, I could do the combination of, let's say we want to actually put these 3 tiles into 2 boxes, and the order doesn't matter. Order doesn't matter, so I would go here and say there's 3 options, there's 2 boxes to put it in, and I could figure that one out, right? In this case, in what we've done so far this week, we've only been trying to find the number of options that we can create by arranging the tiles however we need to. The difference for today is that total number of options, ways we can arrange it, is going to end up being the total number of events that are possible. You see, that's what we're really going to basically find. There's one problem on the test or on the quiz next week that I'm going to put there that will have an option where you have to do a combination permutation on the top and also on the bottom because they'll be relating in a different way. But I think by then we'll have it down. We'll have enough practice to approach that. But today, basically, that total number of events, that's where our combinatorics are going to come in. Okay. Oh, this word also, this just means combination or permutation. Okay, because there's even different varieties of permutations, and this word kind of summarizes all of them. All right, so the basics here, the very, very basics. And when we get to the worksheet that we're going to work on together, so those at home, it is on the iMath. The first 3 are similar to experiment 1. The other 2 are experiment 2. Okay. So looking at this, here we're just dealing with what we already know. This is just basic probability. We know that if 2 events, we want to find the intersection, the probability of those 2 things happening. It's just the probability of A times the probability of B. The probability of one event and the other event. So let's look at our experiment. Pick a card from a 52 card deck randomly. I should add this without replacing. So since we are not replacing it, this situation is dependent because I've taken one option out. Now my options are slightly different in there. Okay. So what are we trying to find for this one? We're trying to find the probability of getting a king of hearts. Good. So here's my 52 card deck. How many cards in here? 52. What's my probability though? Say again. Not just kings. Not just kings. King of hearts is one of those out of 52. And what's that as a percent? What is that? 1 point. Going once.
That's like a 1.92307.
That's
6923.
0.0192. We can also say that is 1.92%.
Yeah.
All right. So we know how to do it for one event. We're just going to add on to that a little bit. How about if I want to get the king of hearts first, and then, let's say, the 3 of diamonds second. I want to get the king of hearts first, the 3 of diamonds second. So this is a dependent event because I take one card out, changes the probability of the second one. But we already figured out the probability of getting King of Hearts first is 1 out of 52. We're going to multiply that by the probability of getting the 3 of diamonds second. Now, I am not replacing the card, so how many options do I have in order to get that 3 of diamonds? How many total possibilities are there? There's 51. I took one card out, didn't replace it. How many cards? The number of ways the desired event can occur to get this is only one way to do it. You have to get the 3 of diamonds. So we get 1 over, what was that, 2650? 51 times 50. No, that's not right. Yes, that's right. No, that's not. Don't listen to me. I'm conflicted. 2652.
Yay.
Okay, we get into a fraction, then we just say fraction is really just a division problem. Go ahead and work that, and we get 0.000377. So that's going to be 0.0377%. All right, is that very common?
No.
Is that very likely? No, right? So if you had your hand to make like a, for this it would be, actually this is a bad hand. If you need a full house, you need these 2 cards to pull up next for you. The chance of that is actually going to be even less than this if you're playing with someone else because they get some cards as well. So thinking about this, probability again helps us make choices. Next week is going to be kind of decision making using probability. So that is what we already know. Everybody feel okay with that? Thumbs up for that stuff, right? Okay, good. All right, now, experiment 2 is where we're going to start to incorporate these combinatorics, okay? So looking at this, I need to find some students here from class. I want to pick them randomly, so I'm going to say, is anybody's birthday close to March 2nd? Danny. Okay, just whoever I see first, no big deal. How about October 17th? October 17th, Camille? All right. How about February 27th? No one, okay. How about June 2nd? June 2nd? July 2nd? So I'm going to go ahead and say this is the probability of, I'm picking them randomly. And what about this part? Probability of getting Daniel, Camille, Maya, getting the flash balls if order matters. Why is the if order matters important? What does that tell us? What are we likely going to do with a combination or a permutation? Permutation. So looking at this, the permutation is going to come into play when I'm looking to see how do I give it to Daniel first, Camille second, Maya third. Okay. First off, looking back over here, the number of ways desired event can occur. How many ways can this situation happen? Not how many options, not how many total number of events, but I want to throw the flash balls out here, right? Randomly, and first it goes to Daniel. Sure. Then it goes to Camille. Oh. Yes! Then it goes to Maya. And everyone caught it, so everyone gets an A.
Yay!
Okay. Sorry, that's a bad joke.
I don't want this.
How many ways could that happen? One way. There's only one way if the order matters, and I need these people to go in this sequence. So there's one way that'll happen. Total number of events. There's a lot of ways I could have thrown those balls out, right? A lot of ways. For it to work out exactly like that, it's going to be pretty unlikely. So I know this number is going to be huge. And what do we say we're going to use to find the total number? Order matters?
Permutation.
Permutation. So I'm going to go ahead and write this over here. So I suggest doing these on the side. Let's see how many students we have in here. I'm going to have to look. 33. Yes. 33 students. We're trying to find the permutation of these 3 students being in a particular order. So we set it up, 33 factorial, 33 minus 3 factorial. Go ahead and do that. I want you to set it up so that you can cancel out one of the factorials on the bottom. Well, the difference of this factorial on the bottom. If you forgot how to do that, I put up over there on the whiteboard. All right, factorial of 8, 8, 7, 6, 5, 4, 3, 2, 1. So I just decide 5, 4, 3, 2, 1. That's factorial of 5. That allows me to cross that out. All right, can somebody tell me how to set up the top of these? How am I going to set the top up? What's a clever way to do it? Who wants to show they're clever? Come on, clever people. Third period. Yes.
Alright, so you do 33 times 32 times 31 times 30 factorial
There we go.
over 30 factorial.
30 factorial. And you did that to be able to,
Just like,
Cross out the 2 30s.
it's gonna,
30 factorials are gone. Good, good. And then this is going to be a really big number. Somebody read it out slowly to me.
okay. Just gonna write it down.
Is that right? Okay. So this number, that's our total number of events possible for this. There's 32,736 ways that I can pass those splash balls out. Okay. So looking at that, I'm going to go ahead and 1 divided by 32, 736. Ooh, that's nice. 1, 2, 3, 4,
That's a
3,
big
4,
percentage.
5. Point. Yeah. 0, 0, 3, 1%. Is that very likely to happen?
No, but it happened anyway.
Kind of happened. I did it birthday way though. I did it with birthdays. All right, I'm gonna close this curtain. We're gonna look at the worksheet now and do a couple of those. Maybe more.
Yeah. The rest of this.
And let's pull this open. Still filming, so let's keep moving through this. Erase this side first. All right, so the problems on the homework are really similar to these this worksheet problem. The worksheet has some combination permutations that go on and happen with the last two problems. It starts out with just basic probability, and that's what you're going to face when you get to the workbook homework tonight. So let's look to see what we have. I kind of show my age here because I did an example with the Dream Team. I don't know if you guys even know what I'm talking about. Do you? You know what the Dream Team is? Silence, crickets. All right, crickets. That's when, there we go. Basically, that's not what I want. That's okay, though. We'll find it. One sec, guys. Oh, I did put it here. So before 1992, that Olympics, they only let amateurs compete in the Olympics.
Oh, yeah.
So remember, in 1992, this was when all the NBA players suddenly were allowed to play in the Olympics. It was like Magic Johnson, Jordan. Let me bring it up. What's down here? So the Dream Team: Scottie Pippen, Charles Barkley, Larry Bird, Magic Johnson, Patrick Ewing, Karl Malone, Robinson from San Antonio. And so I was just excited to give an example that I like. For me, actually. Come on, stop. Stop. There. Hey, you. All right, here we go. So looking at the first problem, so they have more to do with basic probability. So now we can see it. All right. So looking at this, hope we can see it. Roxanne, can you close that shade, please? Okay, thank you. So here's our situation. So the girls softball team just received a box full of all their new jerseys and their pants, so their uniforms. The experiment is to randomly select new uniforms from the delivery box. Okay, so we're looking at some basic probability here. The probability of selecting 2 items and getting 2 pants, I go, that's the probability of pants and then some more pants. How many items do we have in the box all together? I heard it whispered.
22.
2. Good. And then, how many pairs of pants do we have in our set here?
11.
11? Okay. So I know the probability of picking the first pair of pants, the first pick being pants, is 11 out of 22. Now, this is a dependent event because I'm passing these things out. I'm not taking the uniform out. Oh, that's pants. I'm putting them back. That just is silly. So if I pull that pair of pants out, I don't replace it, obviously. What is my total number of items in the box now?
21.
10 out of 21.
Okay, I like that. Give me right to it.
Just like,
Wouldn't you say that 11 over 22 is really just 1/2?
yeah.
Good, that makes it easier. 10, 42, 10 42seconds, and then we end up with 0.238, 23.8%. Okay, so this is just the basic probability because I took 1 item out. Now I have 21 items. The pants, I took 1 item out as well. There were 10 left over, so it's 10 out of 21 for the second pair, 11 out of 22 when everything's in the box. Right? So you have to see also that items are taken away, so we change that bottom number. Right? Oh, the reason I did that is because 11 over 22 is equal to 1/2 to make it easier for us, so we didn't do 22 times 21. That's right. So I say reduce it always to make it easier working these problems out if you can. Okay. That won't change anything about it. All right, let's go ahead and see if I can scroll down with more success. You're going to have to look on your worksheet for those numbers again at the top. I have them here, so we're all good. All right, so next, number 2, randomly select 2 items. The probability that both items are medium. So that's, we'll go ahead and do probability of medium, then medium. So I know I'm going to have, it's a dependent event, I'm going to have two different probabilities I need to multiply. All right, so looking at this, here we have, let's see, random select 2 items, probability plus medium. How many items do we have in the box to start? 22. And then how many were medium? How many? 10? 10 mediums, right? If I select 1 and it happens to be a medium, how many items left in the box? 21. How many mediums left in the box?
9.
Or you could reduce this if you want, or you could go, oh, that's 90 over,
462.
that's what I said, 462. Go ahead and finish that up. Give me that decimal, give me the percent, practice that out. And, okay. And then right away, once you get that answer, I want you to start working on number 3 by yourself. Number 3, randomly select a pair of pants, then randomly select a shirt. What's the probability that they're both extra large? Probability of pants extra large, shirt extra large. All right, call me over if you need some input. Okay, now if you want to check with your neighbor to start at number 3, you need to double check. All right, another 20 seconds as far as you can for number 3. Check your neighbor. If they didn't get it right, maybe see where either of you went astray. Yeah, you can see it. All right, bring it back, bring it back. What did we get for a percentage for number 2? What did we get for that? 19.4%. What?
You just said nice.
That was the one that we did previously. Yep. Okay, number 3, that was number 2. Number 3, what is the probability of, from my pants, getting an extra large? How many pants do we have?
1.
11. And how many extra large pants?
1.
1. All right, how about shirts? How many pants? How many shirts do we have? 11 as well. How many are extra large?
2.
So we get 2 out of 121.
Yeah, what's right?
And 0.0165 or 1.7%.
Oh, okay.
All right. Double check your work with that. Check with your neighbor. I'll give you like 30 seconds to make your correction. This handout is going to be really helpful with what you'll face tonight. Okay, as you do that, I'm going to go ahead and scroll down to the next. Oh, what happened?
Keep scrolling a little bit, it's a new page.
I just wanted to check.
I want to make, but I don't remember.
All right, you guys have the list of people. All right, so just introducing this, we have the Dream Team. As you can see, oh, there it is. We have Robinson, Ewing, Bird, Pippin, Malone, Barkley, Johnson, Jordan. Basically, our experiment is passing out jerseys randomly. Number 4 asks, what's the probability that Ewing, Jordan, and Barkley shirts are selected first? Okay, and it's not given in order. It's just saying that the first 3 we pick out, right? The first 3 are Ewing, Jordan, and Barkley. So we're going to go ahead and work that out over here. All right. So let's look at this. Probability of Ewing, Jordan, and Barkley. So first off, let's ask for the top portion here. How many ways can I end up with that event happening? How many ways? So the desired outcome is that I pick Ewing, Jordan, and Barkley. Okay. I don't care about who's first, second, or third. I just want that event to happen. So this is always more simple than we think. For those selected to happen, there's one way that can happen. I pick those up. It doesn't matter about order. I'm just talking about how many ways does that event happen. There's one way that these 3 are just picked up. Doesn't matter who's first or second. I'm just saying I pick those 3. I grab a handful of 3 jerseys. I pull out the handful. The one way that I can pull out these 3 people is if I grab those 3 jerseys. So it's 1 out of, this is what we got to figure out. So this is where the probability that Ewing, Jordan, and Barkley, the jerseys are selected. I want you to look at number 4 and number 5 and tell me which one is probably the permutation. Which one's the
Order,
perm?
well, I mean, one of them just straight up says in all caps, if order matters. So I think that's permutation. Yeah, I know. I'm just.
If order matters, if you're my sister and you want curly hair, your hair curliness matters to you. You want the order to matter. In the 80s, you would get a perm. Get permanent. I'm just going to keep trying. I know that analogy just
I'm
isn't
starting to
good.
remember it more. I'm
If I
starting
say it 5 times, then
Yeah.
it's good. That's my trick. All right, so if order matters for number 5, that's a permutation. Did the order matter here at all?
No.
No, I just want to grab 3 jerseys with my hand, pull out 3 jerseys, and I hope that they're those 3 people. So this is where this is where we bring in combination. How many people are on the team? Did I have up there? 8. How many people am I trying to select? 3. So let's go ahead and do the combination. 8 factorial. 8 minus 3 factorial. 3 factorial. Okay? Let's go ahead and do that out. I want you to set it up so you can cancel it. Set it up so you can cancel out one of those bottom factorials. Bless you. Nice quiet sneeze.
More people like that.
Those are nice. You can let it out. It's not better. All right, so this is the difference. This is where this lesson is slightly different. We're doing probability. We need to find the total number of options down here, so we use a combination to figure that one out. Can they see it? Kind of. There we go. All right, here we go. Somebody tell me, how do I set up the top in order to cancel out one of those factorials on the bottom? Anybody? Anybody? What do we do? Still doing it? No. Somebody, come on. Show you're clever. Yes, Malik. Good. 8, 7, 6, 5 factorial. Perfect. On the bottom, that gives us 5 factorial. 8 minus 3. And then it's times 3 factorial. Remember, factorials cannot be multiplied together. We can't say this is 15 factorial on the bottom. Cannot do that. Because a factorial within itself, it's just like when we get to summations. You can't just multiply summations together and hope the numbers work out. It just doesn't work. This factorial is its own operation of sorts. So it has different rules with this. 5 factorial on the top. On the bottom, gone. 8 times 7 times 6 over 3 factorial is 6. What can I cancel out here? What else can I cancel out?
That's 6.
6 is gone. 56. So we just figured out this is 56. And 1 out of 56 gives us 1 out of 56 gives us 0.0179, and that's 1.79%. Not very likely to randomly grab into the box of jerseys and snag 3 with my hands, pull out all 3, and it's those people. It's not very common. Less than 2%. Don't even count on it. All right. Let's see. All right. So the last bit here, this last bit, was the key part that we need to remember with this, that what matters?
Order.
Order matters. So I'm looking to get Jordan's jersey first. I'm going to get Pippen second and Bird third. How many ways are there for me to pull those out in order just like this? Jordan, Pippen, Bird. How many ways can that happen? One way. There's only one way that can happen. That's what goes on top. Our desired outcome, how many ways to do it? 1. On the bottom, here we know that since order matters, we're dealing with a permutation. So we're going to go ahead and make it brighter in here.
Maybe this will work.
It actually just makes it glare. Awesome. Psych. All right. So what goes here is how many options there are altogether. Permutation of 8 players. We have 3 selected in order. And permutations are a little bit easier. This is going to be 8 minus 3 factorial. And I looked at what we did before. It's the same numbers, it's just a permutation. So I'm going to go ahead and do that quickly. 8, 7, 6, 5 factorial. 5 factorial on the bottom. Factorial. And that gets us all the way to 56 times 6 is 336. All right, that's part of the answer that goes here. And nice, highly probable answer here. I kept it as 0.29% because if you round up and it's like a domino effect, and it just goes, it's really going to change your like plus or minus error. Okay, so if you end up with the decimal and it's just this rounds this up, this rounds this up, this rounds this up, keep it to the hundredths, and that'll make it more accurate. Okay. All right, how do you feel about this? Thumbs up, sideways, down? Good. Thumbs. All right, so mainly when you're doing the homework, which is in your workbook, page 95, 1 through 9 odd, the first portion is going to have pretty much quite a bit of what we had on this board where it's probability. The last few, you're going to find some permutation combinations in there. Okay? All right, good luck. We'll go ahead and remind the viewers.
Subscribe.
What should we tell the viewers to do again?
I think it's like the subscribing action.
Substitute?
Skype scrub.
Skype scrum. I don't know what that means.
I don't even.
All right, 123rd gets some Oreos. Remember, if you sign up your friends with or without their knowing, you could get those Oreos. All right.